So the next method we're going to talk about is another simple method. It's a fun, easy method, and it's used for data discovery and can be very powerful in informing you about your data. Clustering, there are a whole bunch of different clustering methods. We're going to talk about probably the first one and the most simple one. It's called k-means clustering. It's an unsupervised method. It has very little feedback. The feedback that is given to it is basically the number of clusters that you want, the maximum distance between the clusters, or a distance metric. Why do we want to learn about it? Because as I said, it's really, really simple. It's good for data exploration. It's good for grouping data. It's good for finding patterns in very large data sets. And if you need to automatically discretize some very large data, you could use clusters to find automatic groups of data. You can use it for prediction, but it's most often used for exploration. What we're going to do with clustering is I'm going to briefly show you the algorithm here, and then I'm going to switch to some slides from somebody else that I often use when I teach this in class because it has very nice graphics on it. And so you'll get to see sort of illustrations of how well clustering works and then what we can do to adjust it. But the algorithm is really, really simple. The way it works is you start with a number of clusters, k, this is why it's called k-means. You choose the initial cluster centers. Generally, you pick these randomly and you try to spread them far apart. And for every single data point, you find the cluster center that's closest to that data point. It's literally a for loop. And then once you've done that, you update all the centers to be the average of their nearest data points. And then you just repeat those two steps until they stop changing. And they will stop changing because as long as you have real value data, you're decreasing your error on each step. It might be a local error, but it will eventually stop changing. So I'm going to do something different. As I said, I'm going to move to somebody else's slides that I use when I teach this class in person. And it has some nice set of examples on it. So give me a second here and we will switch what we're sharing. We're coming back. We're going to use some slides from a professor at Carnegie Mellon because he happens to have some really beautiful slides. Yes, these slides are old, but they've got some great pictures on them, and k-means has been around a very long time. So let's look at this data. This data could be easily modeled by a bunch of Gaussians. You could assume that's where it came from. It's just Gaussians in 2D that you drew from, and it looks like there's 5 groups of data, right? Well, can we do something with those 5 groups of data that we could create the clusters and identify using this algorithm we just talked about? One of the ideas he has is that imagine you're installing some software and you're trying to encode and decode the information about this data. It's going to be very lossy data and you only get 2 bits. And you want to say, what can I say about this data that loses the least information? I could just break it into a grid, but that's not the best answer. I could try to break it into something that actually tells you something about the data, like the centroid of the data. So what k-means does in this case, for example, we're going to say, how many clusters do we want? Well, for example, it looks like there's 5 here. We're going to pick some cluster centers. This is the algorithm we just talked about. We're going to look for all of the different data points that are as close to those cluster centers as possible. And we talked about this in the algorithm, but this nice diagram here shows you what was called a Voronoi diagram, where basically you look at, it's breaking the space up into a 2-dimensional area that tells you which ones are closest to each center. And then you find the new center of that data point and you continue this. And that's why I grabbed these graphics, because it shows you how each cluster center moves over time. So it continues. And you eventually converge on something that looks a lot like the original clusters. Now, this red and this purple cluster are interesting because who knows exactly which ones these were drawn from when you really drew them from the Gaussian distribution? But that isn't the point per se, because you don't have a label that says where they came from. You're just trying to identify patterns in your data. And here you've got your 5 patterns that pretty well represent your data. So some questions you might want to ask: what are we trying to optimize? Are we sure it's going to terminate? Are we sure it will find an optimal clustering? How do we start? And how do we choose the number of centers? We're going to talk about how well it does by basically assuming that you can encode and decode from the cluster center by basically looking at the cluster center and then representing all the data from that cluster center and figuring out how far off you are by how far each data point is away from the center of the cluster center. And then the distortion or the loss is how far away you are. And the question is, could you do anything better than the center or the average of the data points and still find a better distortion? And the answer is no, you can't, because the average is always going to be the best answer given that cluster. And I'll leave this math for you to look at later. Another question you might ask is, are we ever going to terminate? And the answer is yes. there's only a finite number of ways that we can partition this data. And as I said in the other set of slides, we're going to eventually run out. It might be a local optimum. It's probably not going to be a global optimum, but we will run out of configurations. So that gets us to the next question. Are we going to find the optimal configuration? Not necessarily. Can you invent a configuration that's converged but doesn't have minimal distortion? Yes. So look at this example here and then try some terrible k=3 configurations. That's converged, but it's probably not what you would have thought of when you said k=3 for this. So what are there some the answers to solve this? Make sure that your data points that you start with are far apart. And as we did with local search, this is essentially a local search mechanism. Do a lot of different runs. So the trick, pick your first center randomly and then pick the second center as far away from as possible as that first center and continue to do that. And I will stop here and leave the rest of the slides online because this has really reached what I wanted to talk about with clustering. But clustering is a nice method. You might end up using it in Space Settlers, for example, if you want to discretize your data. You could use it in general for just understanding very large data sets to try to just get some categories out of that very large data set because the data might be so overwhelming that you can't find the categories. And there are different methods of clustering. The slides talk about a method called hierarchical clustering, but we're not going to go into that in very much detail. Basically, the idea with hierarchical clustering is you build clusters of clusters of clusters of clusters, and then at some point you can break that hierarchy and say, here's the interesting data to us. And I'll leave that to the slides for you.